Hello everyone and welcome back to Causality with Boris, broadcast from Sobolev Spaces. In this video, I'll expand on comparing all treated and all untreated units. Then I introduce three main ideas: getting conditional means from regression models, averaging conditional means to obtain marginal means, and the two-model approach to accommodate difference between treatment groups. Make sure you watch takeaways at the end. There will be a link to the tutorial on how to find expected outcomes of counterfactual treatments, and we will be using two regression models. As always, to receive a PDF with extra material for this video, check out the link in the description. Starting with individual unit effect, we arrive at contrasting all treated and all untreated units. At core of this approach lies the idea of comparing responses to applying and withholding treatment in the same unit. Each unit gets two potential outcomes, one for each treatment alternative. Then the population level effect is a contrast between these two sets of potential outcomes. We contrast outcomes of untreated units with outcomes of the same units as if they were treated. Recall that potential outcomes are random variables. They come with their own probability distribution over the same population of units. We recast the average treatment effect as the difference between marginal risks for all treated and all untreated populations. We can think of the marginal risk as the proportion of population that would have developed the outcome had all units received the same treatment. I'll illustrate this idea using the mosaic plot. Let's draw a square to represent a population of units. All possible outcomes occupy the total area of this square. The outcomes of interest fill some space in it. In relation to the whole space, to the whole square, the space is proportional to the outcome frequency. To plot it, we divide the square horizontally in two parts. The colored area represents the outcome. Its height is the marginal probability of outcome. But I think we need two squares, one for all treated units and the other for the same units but untreated. The treatment effect is then the difference between probabilities plotted in these two squares. You see, contrasting all treated with all untreated is a major development in causal reasoning. It directly addresses the daunting problem of causal attribution, comparability of treatment groups. We're always concerned that difference in outcomes we observe between treatment groups may reflect the effects of other factors. This problem doesn't arise when we use potential outcomes. After all, the same units make up both treatment groups. The same study population, considered under alternative treatments, aligns with Mill's idea of exchangeable units. Indeed, treatment groups have indistinguishable distribution of other factors now. We compare like with like, only one of which is subjected to treatment. Therefore, comparing marginal risks between two identical treatment groups gives us the unbiased treatment effect, and we attribute it to the group membership. And our first lookout is regression model. We like regressions. Regressions link the expected outcome to treatment and pre-treatment conditions. Capital E here refers to the mathematical expectation, often called the mean. Vertical bar shows it's a conditional mean, the expected value of outcome given treatment X and covariates Z. Regression coefficient beta 1 gives us the change in the mean outcome for every 1 unit increase in X given Z. You can pause the video and prove this by subtracting the mean outcome for X from the outcome for X plus 1. Did you get beta 1? That's right, the other terms cancel themselves out. When variable X encodes two groups, regression coefficient beta 1 is the difference in the mean outcome between the groups. Again, you can see this by subtracting the mean outcome when X is 0 from when X is 1. In his 17th century book, Galileo used equations in two ways: to predict response from known parameters and to find parameters from observed responses. Modern-day regression analysis is his second use case. We estimate coefficients beta 1 and beta 2 from observed treatment, from observed outcomes, and values for covariates. Let's apply Galileo's other use case to our equation. For each patient I, with values zi, we find the mean outcome when variable x is 0 and then when it's 1. We keep zi fixed at their observed values in each unit. It means we find the expected outcome with and without treatment. Let's reflect on what just happened. We take responses to treatments and find regression coefficients, and then find the expected response to treatment that we haven't observed. It all may sound exciting, but there is no mystery here. In fact, we assume that. Yes, indeed, we assume that regression coefficient beta 1 is the difference in the mean outcome between two treatment groups, simply by writing a linear regression of outcome on treatment. So, once we know beta 1, we know the difference between treatment groups. But be careful with the interpretation of the mean outcome given z values. Each patient may have a unique set of pretreatment conditions z. Yet the mean outcome for each z is a population parameter. We find the mean outcome for all patients with the same combination of z values. But still we can find the expected outcome for alternative treatments. Once the regression analysis is done, we average conditional means to find marginal means. Let's say we fit a linear regression. It links the mean outcome capital I to treatment x and variable z. For each unit I, we calculate the mean outcome twice, when x is 0 and then when it's 1. We keep zi fixed at their observed values. Then we average the conditional means over the distribution of z values. We average them separately for two values of x. As a result, we obtain two marginal means, E1 and E0, with and without treatment. The difference between E1 and E0 should give us the treatment effect, right? But it looks like the marginal contrast equals to conditional contrast. Both are the same coefficient beta 1. I would argue it's a consequence of the assumption that we made by writing this linear regression down. We assumed that the coefficient beta 1 is the difference between the conditional means. And the algebra of linear models just shows beta 1 coincides with the marginal contrast. Let's take a closer look using the example from the maternal health research. This graph shows infant birth weight by mother's age and smoking when pregnant. Green dots for non-smoking mothers and blue dots for smokers. The dashed lines show the mean weight given smoking history. The difference between non-smoker and smokers is 278 grams. And that's a conditional contrast. It's the difference between two study groups. This graph also shows age is strongly associated with weight. We may write down a regression model that links weight to both smoking and age. It means we assume the effect of age is the same among smokers and non-smokers. But older mothers were also more likely to be smokers. We need two regression models, one for smokers and a separate for non-smokers. This two-model approach finds two separate expected weights given smoking history and age, and it uses two different coefficients for the variable age. The difference between marginal means now involves the average age in the entire study population. The marginal contrast would be different if only one model is fit for both groups. It would coincide with conditional contrast. The next graph is crucial for understanding the counterfactual nature of our calculations. We have one regression line for non-smokers and a separate line for smokers. Hollow squares show the expected weights. Blue squares for smokers had they not smoked, and green squares for non-smokers had they smoked. The dashed lines show marginal means for the weight at birth by smoking habits, if all smoked versus no one smoked. The marginal contrast between non-smokers and smokers is now 376 grams. Watch my step-by-step tutorial for this calculation. Link in the description. And now let's turn to the averaging of conditional risks. We start by calculating conditional risks from a previously fit model. Let's say we fit a logistic regression that links the outcome probability to a single variable z. Then probability that y is 1 given z is equal to inverse of the exponential of negative beta naught plus beta 1 times z, all added to 1. Then unit I, with observed value zi, has the expected outcome probability capital Pi. It's often called the risk of outcome, and it's a conditional risk for given zi. A set of n units has a set of corresponding conditional risks. Our next step is to average them over the z values. Marginal probability for y is 1 over the distribution of variable z is simply summation of the products of conditional probabilities p of z and the marginal probability for z values. Again, we average the conditional risks calculated from a previously fit model over z values in the entire study population. If a distinct value z appears nz times, then probability p of z will appear in z times 2. For a large number of units, the average conditional probabilities will be close to the marginal risks. Now let's fit a model with two variables. One is treatment x, the other represents pretreatment factors. For each unit I, we calculate the conditional risk twice, when x is 0 and when it's 1. We keep zi fixed at their observed values. We then find marginal risk by averaging conditional risks. We average over z values in the entire study population, and we do it twice, separately for each value of x. As a result, we obtain two marginal risks with and without treatment. Of course, we assume the distribution of z represents the population. If it's true, there are two counterfactual cases here. First, marginal risk as if all units are treated. That's unconditional probability that y is 1 for the entire population were it to undergo treatment. Second, marginal risk as if all units are untreated. That's unconditional probability that y is 1 for the entire population unexposed to treatment. The difference between P1 and P0 is the treatment effect. The main message here is we find the expected outcome for each unit in the study population. We use a fit regression equation with unit-specific variable z, and we do it for all units. And we do it twice for two treatment alternatives. We use the expected proportion of units with outcome to see if there is a difference between two counterfactual populations. All units undergoing treatment of interest and the same all units remaining untreated. Make sure you watch tutorial for this video. I walk you step by step through calculations of the expected outcomes for counterfactual treatments, and we will be using two regression models. Keep on watching.